Bonjour. This is the fourth video in the Introduction to Probability chapter, and in the last video we saw how we can draw probability trees, including uh, if you have multiple trials, how you can have uh, branches at each level, and you can draw the probability tree, and then it becomes easy to calculate the probability of events such as 3 heads in this particular case, or getting at least 2 heads, or as I asked you in the in-video problems, getting exactly 2 heads and getting exactly 1 tail. In this video we will start with showing that it is not always necessary to draw every branch of a probability tree. For example, let's calculate the probability of getting 5 heads in 5 coin tosses. Remember, right at the beginning, in the first video itself, at the beginning of the first video, I mentioned that what is the probability of getting 5 heads in 5 coin tosses, and I told you it was 3.1%. Well, now we'll see exactly how it is. So if we draw the probability tree, then we have to draw 5 levels, because we are tossing the coin 5 times, but we are only interested in the heads when each sequential toss gives me a head. So what we do is we ignore these other branches, and we only go along the one branch that we are interested in, and we know that the first time we toss it, we have a half 50% chance of getting heads, and the second time we toss it, we have a 50% chance of getting heads, and so on. It's always 50%. There is no concept of memory. The coin doesn't remember what has gone before. Each of these is an independent trial. So in each case, it's an independent toss. So in each case, the probability is 50%. So to get 5 heads, you will have to multiply this 0.5 into 0.5 into 0.5 into 0.5 into 0.5, which is, let's define our event, 5 heads in 5 tosses. So I should write 5 coin tosses. So we get probability of E1 0.5 into 0.5 into 0.5 into 0.5 into 0.5, that is equal to 0.5 to the power 5, also equal to 1 over 2 to the power 5, which gives us 0.03125. So this is a probability of getting 5 heads in 5 successive coin tosses, and this is the same as 3.125. So this is what I had said in the first video. If I do this experiment 1000 times, I should expect to get heads, 5 heads, 0.03125, that's the probability, into the number of experiments, that is 1000, that is 31.25 times. And if I done it 100 times, if I just want to actually make sure how I'm calculating the percentage, then we have, if I do it 100 times, 0.03125 into 100, it gives me 3.125, so which is approximately 3.1% of the time. So whenever you're doing this experiment of tossing the coin 5 times, and if you do the experiment 100 times, about 3 times here, you should get 3 out of those 100 times, you should get 5 heads. Okay, so now we move on, and so far we have looked at trials or experiments that we have done where it's the same thing. We are tossing the same coin, we are tossing the same die, we're pulling out a colored ball from or a numbered token from a bag, but each time we are doing the same experiment. Now we can have combinations. We see how we can have combinations of different trials and events. Events is not the correct word. I should actually write experiments, but here we go. So I have two bags. Both are opaque, that is not transparent, you cannot see. This one has two colored balls and one white ball. This one has one colored ball and three white balls. So I will first take out a ball from here, and then my second trial I will take out a ball from here. So if first you take one ball from bag 1 and then one from bag 2. So if we draw the probability tree, the first part will have to be for this and the second part will have to be for this. So let's start here. So if I draw it, so here you can see I have one white, two colored, so 1/3, one out of 3 times I should get white, 2 out of 3 times I should get colored, and of course 1/3 plus 2/3 has to add up to 1. So now the second time, now we are taking from the second bag. So once we have got a white ball here, or indeed a black ball, or colored ball rather. So here if we take, what is the chance of getting a white ball? That is 3 out of 4. So to get a white ball, it's 3 out of 4. To get the colored ball, it's 1 out of 4. So to get two white balls, that is one white ball from here, one white ball from here, you have to multiply 1/3 into 3/4. So two white balls, 1/3 into 3/4, which gives us 1/4. So if you do this experiment, 1/4 of the time you will get two white balls. Okay. So if the first time we get a white ball, the second time from here, the second bag, 1/4 of the time you will get black ball. So to get white ball first, white ball from this and a black ball or colored ball from that, you will get 1/3 into 1/4, which is equal to 1/12. So the probability of drawing a white ball here and a dark ball there, colored ball there, is 1 in 12. Similarly, if we draw a black ball from here, we are just going to copy this again here, 3/4, 3/4, white ball, 1/4, 1/4, black ball. So here we get first a black ball and then a white ball. So here it is 2/3 into 3/4. 2/3 into 3/4 is equal to 2/4. The 3 and 3 cancel out. So you get half. So 50% of the time when you do this experiment, you will get one black ball in the first bag and one white ball in the second bag. And similarly, if you the probability of getting two colored balls, one from here and one from here, is 2/3 into 1/4. 2/3 into 1/4 is equal to 1/6. We can do a verification. We can add up all of these probabilities and we'll get 1/4 plus 1/12 plus 1/2 plus 1/6. If you do it, you will see it does equal 1. You can take the least the common denominator as 12, so you'll get 3 there, 3 plus 1 plus 6 plus 2, it will give you 12. 12/12 is equal to 1. So here we can now, if I defined an event E1 as getting two balls of different colors, so two balls of different colors are only this case and this case, so you have to add up 1/12 and plus 1/2. So you add up 1/12 plus 1/2, it's 7/12, so 58.3%. So you have a 58.3% in this particular experiment of getting two balls of different colors. Now remember, I've shown you this because we are taking the first trial is of one random event and the second trial is of another random event. Okay, so in these cases, in all the cases we have seen so far, the first where we are doing two experiments, or whether the experiment consists of two parts, every one is independent of the other, of the two experiments or three experiments, or as in this case we did an experiment with 5 tosses. Each one is independent of the one before or any one before. So these are, each trial is independent of the others. Example, 2 tosses of a coin, 3 throws of a die, each time you throw it, you have a 1 in 6 chance of getting any particular number. Two trials of a pinwheel. I call this a pinwheel, so with the pin in the center. If we rotate it, whether we do the fifth time, when we do this, it is independent of what has happened the 4 previous times. And the example above, this example again, what you do here has no bearing on what you do here. The outcome of this experiment, this part of the experiment, has no influence on the outcome of this part of the experiment. Okay, so you have to realize that when you do an experiment or 2 or 3 or 4 or n parts, that in most cases the trials are independent of each other. So for each one you can calculate the probabilities of outcomes without worrying about the configuration or the situation of the previous part of the experiment. Okay, but there are some ways where the trial is dependent on what has gone before. So this is known as, and we'll come to that, it's very simple. This is known as dependent trials or events, and it's known as conditional probability, where the probability depends on what has happened before, on the condition that took place before. So let's take a very simple example. I have this bag with 2 black balls and 3 white balls, and I ask you to take out 2 balls. You put your hand in and you take out 2 balls. Now that is the same as you putting your hand in and taking out 1 ball, and then again putting your hand in and taking out a second ball without putting back the first ball in. So have you understood this? That if I ask you to take out 2 balls from here, it is the same as saying that you take out 1 ball and then you take out a second ball without putting the first ball back in. So you take 1 ball from the bag, then without putting the ball back, you take another ball from the bag. So in this case, because the condition will change of the bag depending on which color you take out first, the second part of the trial is dependent on the outcome of the first part, and this is what we will do. This is a simple way of looking at it. So let's do the first part. I'm taking out 1 ball. There are 5 balls in total. There are 2 colored balls and 3 white balls. I have 2 out of 5 chances, probability of 2 over 5 of getting a colored ball and 3 over 5 of getting a white ball. But now that I've taken out a black ball here, what does the bag look like? The bag looks like this. The 3 white balls are still there and there's only 1 black ball left. So now there's a bag with 4 balls. Initially we started with a bag with 5 balls, and now we have a bag with 4 balls, 3 of which are white and 1 of which is black. So now what is the probability tree of this part of the trial? 1/4 will give you black, 3/4 will give you white. So if we look at this, we can see that the probability of getting 2 black balls, first a black ball and then a black ball, is 2 over 5 into 1 over 4. 2 over 5 into 1 over 4 is equal to 1 over 10. You'll see it's 2 over 20, which is equal to 1 over 10. And similarly, to draw the first ball black and the second ball white, black and white, you will have the probability 2 over 5 into 3 over 4, and here you will get total of 6 over 20, which is 3 over 10. But what happens if you drew a white ball first along this branch? So when you drew a white ball first, what was left in the bag? What was left in the bag were 2 white balls and 2 black balls. It is different from there where there was only 1 black ball and 3 white balls. Here there are 2 black balls and 2 white balls. Now, if you have an equal number of black balls and white balls, the probability of getting a black ball is half. The probability of getting a white ball is half. So if you, what is the probability of first getting a white ball and then a black ball? So that is 3 over 5 into 1 over 2, 3 over 5 into 1 over 2, which is 3 over 10. And similarly, what is the probability of getting a second white ball after you have already pulled out a white ball? That is 3 over 5 into 1 and 1 over 2, the same as this indeed. You get 3 over 10. If you add up all of these 4 probabilities, you will come up to 1. 1 over 10 plus 3 over 10 is 4 over 10 plus 3 over 10 is 7 over 10 plus 3 over 10 is 10 over 10, which is equal to 1. Okay. So now, this is the in-video problem for this. And here you have to say, getting 2 balls of different colors is the event 1. So what is the probability of event 1? And event 2 is getting at least 1 black ball. What is the probability of getting this event? What is the probability of this event? And this event is defined as getting at least 1 black ball. Okay. So I think we will stop this video here. Now we have enough knowledge to do all the problems in this chapter. Indeed, I don't think that the book has covered dependent trials and experiments, where this second experiment, it depends, the outcome of the second experiment and the probabilities of the second experiment depend on the probabilities of the first. So you see, in this particular case, when I had 2 separate bags, each independent of the other, the second experiment here, 3 over 4 for white, 1 over 4 for black, remained the same, 3 over 4 for white, 1 over 4 for black, irrespective of whether you pulled out a white or a black from the first bag. Here you see it's different. If you pull out a black first, then you have 1/4 chance of getting 1/4 probability, 1 over 4 of getting black and 3 over 4 of getting white. But if you pull out a white first, then the probability of getting a black changes from 1 over 4 to 1 over 2. Indeed, it doubles. And here also it changes from 3 over 4 to 1 over 2. So these are dependent trials where conditional probability is involved. Okay, I will stop here, and this will very likely be the last video for this chapter, except there is a very interesting problem of probability which confuses many people, and it comes back to my original statement that if you know maths well, you will make better decisions in life. And that this is so counterintuitive. What does it mean, counterintuitive? It seems so contrary to common sense, but it can be mathematically proven. I will show you the results of one experiment which has confused people for many years, including many intelligent people. But mathematically, through probability, it can be shown that the result is something totally different from what we expect. I will make that video a little later on. Now we will concentrate on doing the problems in this chapter. Okay, I stop here.